Hello everyone. Hope you can hear me. Um,
Yes, sir.
okay, yeah. So let's start today's session. I am sharing my screen. Okay. Yeah. Okay then. So we'll be discussing a few things based on week 10 lectures, and then we'll do questions based on the discussion. Okay. So what was done for week 10? I guess this was a really long week as far as I know in terms of the video content out there. So how did it start? What was the main topic of this week? So it was introduction to machine learning. I hope people are remembering that. Okay. So this week was mostly about what are the machine learning techniques used in general and also to some extent in computer vision. So since why do you think, first of all, I'll ask you, why do you think we need to do this topic in a course of computer vision? Anyone? So what have we done till now? If you can say briefly, then you can understand why we need this topic here in this course. So mostly whatever we have done, we have used maths, right, to characterize anything or to try to understand any aspect of it. For instance, trying to understand how the camera motion is there, or understanding what are the different uh, content in the image, whether it's low frequency, high frequency, and to some extent even segmentation based on just what maths gave us to some yeah. But we have not really generalized it to other aspects in the sense now for segmentation, for instance, if you use a particular threshold for a one image, you cannot really use the same threshold for other image, right? So whatever we have done till now is based on what we just see the data as it is and not really trying to learn from it. The one exception is the PCA, where we try to get eigenfaces from the data that we have. But apart from that, I don't remember clearly of any other example that we did, which is just based on which learns or tries to generalize whatever we know about things. So since computer vision also deals with the aspects of perception, so we need to learn a few things that can't be mathematically defined. So that's why this topic is really important. And most of the current algorithms, the new algorithms, are developed based on the machine learning uh, concepts. So it's good to know machine learning in this specific course. Okay, so how did it start? I mean, the definition of artificial intelligence was given, and then machine learning is a subset of artificial intelligence, and the current boom of deep learning lies within the machine learning part. So the deep learning, why is it called deep? Can anyone tell me what is so special about deep learning? So no answers. What is so special about deep learning? What happened suddenly? If people know that things, basic structure of neuron, artificial neuron was developed in 1960s or 1958, and since then things have been there, but what suddenly happened that led us to deep learning? So one of the main reasons is, of course, the availability of data, because through internet we are able to share data as much as possible and very quickly. So more data means you can able to find patterns out there from the data very easily. So that's one of the reasons, and the other reasons is compute power. So just 20 years back, whatever compute you have on your phone was not even on a PC out there. So the amount of compute power has also increased, so we are able to process more data quickly. And of course, the availability of data helped it to gain momentum. And that's why deep learning is one of the most preferred methods these days for developing your algorithms. Okay, so what is what is the main aim of machine learning as such? It tries to find patterns in the data. So once you are able to find some pattern, it can try to generalize on unseen data out there. That's the whole class. That's the whole idea. So what are the three different tasks that you can do using machine learning? Anyone? The three main tasks that were discussed in the lectures. First is the classification, that given data point, you want to classify whether it belongs to which class. The second one is regression, where instead of uh, getting classifying a data, we try to get parameters which generalizes the data. So that is regression. And what is the third one? The third one is clustering, which was also seen before in PCA, but here we again go through it in some other aspects as well that will come as we go through. Okay, so the what do you think the most important step of these machine learning systems are? Anyone? So the most important step is the feature extraction part, because if you don't have useful enough features, you may not be able to make sense of the data. I hope that's quite intuitive. And yeah, most of the whole theory that we developed and that was developed in the lecture was based on the fact that we are able to get good features from the data. So the features could be as simple as edges from images or as complicated as detecting an object in the image. So yes, feature detection is very important part of it, and I'll give you a nice example as we go through. And then plus then a few discussions were done on classification, which is based on the Bayes theorem. So what is the Bayes theorem? The Bayes theorem is very simple, but in terms of classification, what it says is you are trying to predict the class. This is the class label, and this is given data or given a point, given a data point. What does it say? So what this term is, this is class conditional density, and this is the prior term that whether you know how much occurrences of this class happen, and the term in the denominator is the evidence that what is the space over which your input data even exists. It gives you a characterization of that. So this is the Bayesian classification approach. So for most of these cases, you assume that your densities are parameterized. For instance, Gaussian density is there, then you can easily get the mean and variance and try to model this posterior density. So given this, there were a few examples given in the lectures. There was another set of classification of the methods, which was given like this. So there are the first set of classification is deep versus shallow methods, where deep means you have many more layers of compute units out there, but shallow means there are very less units of computation. And then on top of this, there was unsupervised versus supervised learning. Yeah, and then there are methods which directly use probabilistic approaches, probabilistic versus non-probabilistic. Okay, so what is supervised learning? This is the most common method used currently for developing algorithms. So what do you mean by supervised learning? So for supervised learning, what happens? Yeah, someone is saying.
Supervised is provided with the data set
Uh,
input. As an input.
so in all the cases, you should have some input. So you have data sets out there. Something else is extra.
Train the data with labeled data. मतलब, train the model with labeled data.
Yes. So your data contains the labels as well, not just the inputs. It contains the expected output as well. You can, I mean, that's generally called as labels. So for the supervised case, this contains labels or outputs, desired outputs, and in unsupervised case, it doesn't contain the labels. Okay, so since and what is there is another classification which doesn't really fit into this. Yeah. Okay. So the other classification is what? Can anyone guess? It is reinforcement learning. What is reinforcement learning? So the problem there is that you don't really have a set of uh, input-output relations, direct input-output relations. For instance, whatever there is a robot has to do to take maybe use its arm to hold a cup of coffee. There is no specific way in which it can do it. There are multiple ways in which it can do it. So the aggregate aggregate of the actions gives you the output. So that there is no specific optimal way on how to get that cup. You can either hold the cup directly, or you can just turn around and then hold the cup indirectly. The point is, the final answer that we need is holding a cup from that robot, for instance. And it's mainly used in robotics these days. Of course, there are other applications as well, but that's the current hot field where it's applied. Okay, so whatever we did till now is mostly extract features manually, like shift features, hog features, and then use some sort of uh, mechanism which we did not discuss in detail to classify things. For instance, one could be the k-means algorithm that was discussed. But with this deep learning era, everything, including feature extraction, is done using a neural network module, which uh, in practice gets better results than the handcrafted features that we discussed till now. And why do you say so? Is because there are many things that we cannot mathematically formalize. For instance, for shift, we have defined so many things and so many tricks out there to make it scale invariant and notation invariant. But it is, but after a limit, it really doesn't work. Even for scale, even if you change the scale, there are thresholds to it, how good it can generalize to differences in scales or rotations. But in deep learning, you try to extract other features as well. They are not just features based on patches. There may be features which are image level, for instance, which helps them to get priors on for what kind of images, what kind of features needs to be extracted. So deep learning methods are generally preferred these days, specifically for extracting features as well, and not just in terms of for computer vision, but for other fields as well, including speech processing, yeah, and maybe medical signals. Okay. So given this, there was a very short discussion on what is underfitting and overfitting. Can anyone tell me that? What do you mean by underfitting or overfitting? What happens in an underfitting situation and what happens when the model is overfitted? Anyone? What is underfitting? As you can see, it's under something, right? So any guesses just by name? Well, these were discussed in the lectures, if you remember. That is good enough. So for underfitting, what happens is if you have a set of data points like this, probably this looks like a parabola to me. Yeah. So data, if you took a linear model, then it might fit like this. Because linear model means there is only a line that you can fit on this 2D data. But if you have a polynomial, probably fifth order polynomial, this is linear order x polynomial. And if you have a fifth order polynomial out there, this will be order x5, x to the power 5. So what you see, there's too much uh, there's too much change in this curve. So it means that when you overfit, you are trying to fit the noise in the data points as well. But when you underfit, you're trying to fit, you don't have enough expressibility. Your model doesn't have enough expressibility to fit this set of data. So this is also one of the big challenges in machine learning, that is choosing the right model. So one of the biggest challenge that we discussed earlier is choosing a correct set of features, which will come back again. And then this is also another challenging aspect of it is choosing the right model. If you don't choose the right model, it's possible that you are either underfitting or overfitting. So given this data points, what would be the optimal curve that at least we think is like this? So there would have been a parabola from where these points are generated, and from this generated points, we are trying to fit back the parabola again. So this is what the pattern is. The parabola is the pattern that actually existed, and we are trying to rediscover that pattern. That's why this machine learning is called as pattern recognition as well. Okay, so what happens? How can you detect that you are underfitting? So you divide your data into train and test samples. So in underfitting case, what happens? Anyone? What happens in underfitting case?
The training data will exactly match, but the testing data won't match.
No. For underfitting, is it the case? So you can please
It's
see
opposite.
clear. Yeah, it's
Vice
opposite.
versa.
Yeah, so you can see clearly that your training data doesn't fit properly, neither your test data fit properly. So given these data points, the black dots out there, you take some of them as training data and some of them as testing data. So you can see that both of them don't fit properly with this model. Specifically here, in this case, it's a linear model and it doesn't generalize well to this data points. So we call this as underfitting case. So the overfitting is what you said, that when you have a set of data points, your training data will have low error because it fits exactly to the data points given to us. But when it comes to test data, maybe here one test data is here, one test data is here. So, or if one test data is here, it's quite far away from the curve, not actually from the curve from which it's generated, but from the curve that we estimated, it's quite far away because there is too much variation in the curve. So it's overfitting. So how can we detect overfitting? That the test accuracy will be very low, but the training accuracy will be very high. So I'll write it here. Training accuracy is low here, and test accuracy is low for the case of underfitting. And here training accuracy is high, but test accuracy is low.
Look,
And what about this case? Optimal model.
the both training and testing will be optimal.
Yeah, so both training and testing accuracies will be high. So all these things are assumed based on the fact that you can learn the model. Of course, learning means you have to solve an optimization problem there. And we assume that you are able to solve the optimization problem, and in that case, we can generalize it in this to in these three types of models, whether it's an underfitting model or optimal model or overfitting model. Okay. Okay. So yeah, these concepts are generally coming from statistics and not specifically new to the people. It's just that it's been applied to the machine learning context as well because there's so much overlap with statistics. Okay. So now coming back to features. So as I said that feature extraction is one of the most important part of the pipeline if you want an end application, maybe classification of objects or species. And one of the examples given in the lectures is about fish classification, which type of fish it is. So, so I,
Sea of salmon.
yes, yes. So, I mean, you can use any other example, that's not a problem. The point is, I want to highlight the importance of feature uh, extraction. So, I have this specific case where x1 is one feature and x2 is other feature for a given classification problem. And what I have is this is one of them, and this is another set of features here. Okay, what do you think is this? Can you say anything about the features x1 and x2? Visually seeing it?
By linear function, we can divide it.
Okay,
Linearly separable.
yeah, this, for instance, is one of the linear classifiers that can separate it. Okay, anything else? Anything else that you see? If I ask you which feature is useful, x1 or x2, what would you say?
This one,
X1 is useful. Why?
because we can separate
Hmm? We can?
classify it properly.
Yeah, you can classify properly. That means the discriminative power of feature x1 is very high, and there is no discriminative power in feature x2. If you can see here, uh, yeah. So if I draw lines here like this, there is no line which can divide both of them, both the classes using feature x2 only. So that's why the discriminative power of feature x2, there is no discriminative power in this example that I gave, but in the example for x1, it is way too much discriminative that if you just extract feature x1, you're done. You don't need any other features. But if you extracted feature x2, it is useless. You can just throw it in dustbin. Okay. So it is very important to get the right set of features. Of course, this is something ideal that you generally won't find. Your general features would be of some kind like this, probably. In real life, it can look like this. So again, you can divide it, but it is not linearly separable. So what you can say is you need a nonlinear classifier to separate the data. Yeah, you need a nonlinear classifier to separate the data into two classes. Okay. So can anyone tell what would you do here? How do you proceed with such kind of data? Because this is what you actually get in the real life.
We can increase the feature that is hyperplane. We can use hyperplane rule
Okay.
classify. Increase the dimension.
So what do you think can help with increasing the dimension?
Uh, when we increase the dimension, we can separate it using plane. Instead of this line, can separate it with a plane.
Okay, that's one possibility. Another possibility. The other possibility is what was discussed and what we are discussing, that is discriminant functions, which can easily tell whether it belongs to a specific, given a data point, it belongs to a specific class or not. So yes, one of the ways is to handle this is uh, people use the word project the data into higher dimension, but I personally don't like that word to project data into higher dimension. Anyways, so I would like to use the word lift the data into higher dimension. What is the assumption out there? Uh, so we are hoping that the data in higher dimension is what? Linearly separable. Or else you can use a nonlinear model to solve this problem, which is uh, the nonlinear model could be uh, like discriminant functions that we'll discuss now in some time. So if you can directly model this curve, so you don't need to project it into higher dimensions, or else you have to cleverly project it into higher dimensions so that it can take care of uh, whether it's a linearly separable data point in higher dimension or not. So this specific part is sometimes tricky, and sometimes nonlinear model designing a nonlinear model itself is tricky because, as I said, it's very non-intuitive sometimes to choose which kind of model to use for given training data, and you can face the problem of underfitting and overfitting. So you'll try to see whichever works better for you and then choose that specific kind of model. Okay, so once this was discussed, and then there were a few things discussed about model choices, and then it comes to clustering. What is clustering?
Now we can group into clusters which belongs to C type.
Okay, so what kind of data do you use for clustering? So you generally don't have labels, right? What you
Yes.
have is just the input data. You don't have an expected output data out there.
Unsupervised.
Yes,
Like,
yeah, yes, you're right. It's clustering generally comes not generally. It comes under unsupervised learning. Clustering comes under unsupervised learning. Yes. So as you said, yeah, we want to divide the data into some meaningful uh, classes. So that's why we use clustering, and it's an unsupervised learning. We'll uh, go into the specific one of the examples that we did, rather algorithms that we did is PCA, principal component analysis, and we'll also look into the LDA as discussed in the last lecture of this week. So the main problem with clustering is it is subjective. So what do you mean by subjective? One good example given in the class is given a bunch of people. If a child sees it, then he or she will divide the bunch of people into whether they belong to the family or not. But if someone who maintains a database of the population, they might see it whether uh, they might distinguish the same set of people into females or males. So that's another way. So it's quite subjective based on what application you need. And so the again the same point comes back is what features should you use to get a good discriminative power based on your specific application. So the attribute, whether it belongs to a family or not, was used by a child, but the attribute, whether the gender of the person is female or male, is something used by a database manager. So based on the applications, it is very important to choose what specific features you need. Okay, so one basic algorithm was again given is the clustering, k-means clustering algorithm, which was discussed in earlier lectures. So we'll just skip through that. So there's one specific topic that everyone asks in interviews, so it is really important, is empirical risk minimization. What is empirical risk minimization? Can anyone tell that? What does it mean? So empirical means whatever the data that you see, you can only use that. You don't have the full data, uh, at least during training part. So whatever data you have to use that much information to train your model. So that's why it's empirical. So risk minimization in general means you want to reduce the error rates, for instance, to misclassify an object from one class to the other. That's why that's risk minimization. And the risks may not always be equal. For instance, if you uh, maybe, how do I put it? Classifying a pencil or a pen doesn't have much of a risk. Both have same amount of risk because you if you either carry a pencil or a pen, you can still use it to write it on a paper. So that's fine. But if someone says that if you want to classify a dog or a cat, it could be it could classifying misclassification might have more effect on one rather than the other because it's possible that you cannot use the vaccines used for dogs for cats. So the vaccines which are denoted for dogs may not be used for cats, but the vaccines used for cats may be used for dogs. So the risk changes automatically based on how much uh, misclassification impact you have. Okay. So given this, there are a few things that were also discussed, which was true positives, false positives, and the other things, receiver operating characteristics that we won't discuss through in detail. But yeah, we have already discussed about true positives and all in one of the previous lectures. So one of the main, so here empirical means using just the data available. Uh, no idea about underlying distribution of the data. Of course, we make assumptions, but that doesn't mean that we know what the underlying distribution is. And risk minimization, as I told, we want to minimize error rate. So that's the whole idea of empirical risk minimization. Okay, so coming back to classification, since that was discussed in depth in the first lecture. So there are two forms of classification, two types, two ways in which you can do classification. One is generative classifier, What is generative classifier? Anyone? So the generative classifier means you have an idea or try to get an idea of the distribution of the distribution. For instance, you assume Gaussian distribution, and then based on that, you try to estimate the parameters of the Gaussian distribution, which is the mean and the variance. So once you estimate the parameters, you can also generate data from the given distribution. That's why it's a generative classifier. What is discriminative classifier? We don't model the distribution. What what we do instead is directly use the data given to us. Of course, both of them involve the probability distributions, but in one case we explicitly model it, and in the later case we don't really try to model it explicitly. Okay, so given this, there was an important topic that was discussed, which is linear regression. What is linear regression? We know what regression is, right? We have both input and output labels, input data and output labels, and then we want to find a relationship between the two. That is regression. And what is linear in that? You can just speak out. Don't.
Finding
Yeah,
the best fit line for the data points.
yeah, line or any hyperplane in general. Yes. So yeah, people can just unmute themselves and speak because I don't really see the Google Meet screen always. Okay. So yes. So you have to fit a linear model. That's what linear regression means. So you already have the data xi comma yi, maybe n data points out there. So what you need to do is you need to fit a linear model. So in 2D case it's fitting a line, in 3D case it's fitting a plane, and in ND case it's hyperplane, well, n greater than 3. Okay, so we'll be doing one example, one question based on this. So I think we can discuss there more instead of discussing now. Okay. So based on Bayes theorem, there are two. There is maximum a posteriori estimate, and one is the maximum likelihood estimate. So maximum likelihood estimate, what do you do? For classification, what do you do? What is the quantity that you want to use for maximum likelihood estimation in classification? You want to get?
Parameters.
No, that's okay. That is something that we choose to do. What we actually want is we want to get this distribution probability that the probability of a data point given a class, given a class I. That's what we want to estimate. Of course, for this case, we generally use parametric methods like we assume this to be a Gaussian. Uh, we assume this to be Gaussian, and then we get the mean and variance of the Gaussian. But the whole idea is what we want to get is probability that data point X occurs given a class. So this is what is the class conditional uh, distribution that we looked earlier. Okay, so what do we want in map estimate? Maximum a priori, a posterior estimate. So here we use Bayes rule or Bayesian estimation. That's why it's called as Bayesian estimation. So what do we do is probability of Wi given x. That means what we want is probability that we assign class x, sorry, class Wi given a data point x. Okay. So just for clarification, where does x lie? Is it discrete or continuous? So it can either be discrete or continuous. For the examples that were given in the class, it is continuous. And what about Wi? Wi is discrete or continuous? They are just class labels, right? Class labels are always discrete. Okay. So what Bayes uh, Bayes classifier does is, can anyone tell me that? Bayes classifier? Classify X as Wi if probability of Wi given X is greater than probability of Wj given X for all values of I not equals to j. Is this clear? Is this statement clear? So if your posterior probability for the given class is higher than all other classes, then you just assign the point x to belong to class Wi. That's what the Bayesian classifier is. And what is actually doing is it is minimizing the probability of error. Well, the probability of error here is misclassification. And to be specific, it is minimizing it under the case where you take 0, 1 loss. 0, 1 loss means if the classification is there, if it's misclassified, you assign a loss of 1. And if you classify it properly, you assign a class of 0. So this was same as that of lambda ij or alpha ij that was used in the class. I don't remember the notation. Okay, so this is alpha ij and not lambda ij. Yeah, so this is the alpha ij that was discussed in the class. Or sorry, alpha is the action there, and lambda is the loss done. Okay, so given this, we have this classifier, and this classifier can also be seen as a discriminant function. What is a discriminant function? Anyone? So again, it's the uh, same way you can say that if gi of x is greater than gj of x for all values of I not equals to j, where I and j are classes, then assign wi to the data point x. So that's what it is. Or you can easily define another function. Maybe I'll just write it as capital G, with this gi of x minus gj of x, which makes sense when there are two classes. Then this will be g1 of x and this is g2 of x. And if it's now greater than 0, you assign it to class I. And if it's less than 0, then assign it to class j. Uh, yeah, for two class case, I means class 1 and j means class 2. That's it. So that's how you can use discriminant functions. And yeah, there are many more things that were discussed in it. We should skip them quickly. So all these things, when you use Bayesian classifier, you assume that there are parametric forms for this. For instance, you can take this as Gaussian or any other uh, specific distribution and work with it. But there are non-parametric techniques, non-parametric distribution.
Does the does the discrimination function perform the same as the Bayesian classifier, or is there any difference, like in functionality or something?
So discriminant function is a general way to describe things. Bayesian classifier is one specific way of checking with posteriors or with specific weights lambda ij. But discriminant function is a very generic method. It's not the you can write this specific thing as a discriminant function by just taking the difference between the two posterior probabilities. But discriminant function can be applied also for non-parametric cases. Okay.
In case of multiple classes, like in terms of how we classify the data points, which one would be used, like discrimination function or Bayesian classifier? Like discrimination function uses only two classes at a time.
No,
So,
not necessarily.
okay.
So these are the set of discriminant functions, GIs or GJs. This is for two-class case, I can write it as G of X. For multi-class case, you cannot really write G of X like some specific function. So yes, for discriminant functions, you have to check for all possible combinations of classes, and then you have to decide which one has the highest value for the discrimination, which gives you the final answer, which class it belongs to. So yeah, all these things are generalizable to multi-class case, even the Bayesian classifier. This is what I wrote the definition for multi-class and not for single class. So this specific quantity what I write is for all values if I not equals to j makes it multi-class. Okay, so then we come to the non-parametric estimation. So what people have done in non-parametric estimation is uh, yes, someone pinged me. Okay, yeah. So what do you think? What's done in non-parametric estimation? So of course now again you need to find a probability function p of x, but you don't want an explicit form. No explicit form is there. So the two methods that are used is two generally used methods is parse and window method and k nearest neighbors. Okay, so what is parse and window method? So intuitively what you do is you divide uh, so I'm giving just an intuition so that we can quickly skip through this. And this is k nearest neighbors. Okay, so for Parson window, what you do is you fix the number of, you fix the uh, amount of volume there. For instance, if these are the data points, the dots are the data points, you fix the volume and see uh, how many data points are there in that volume. And given this, your probability of x in the neighborhood of this point is given as k by n upon the total volume V, where k is the number of data points in this volume, N is the total number of data points in the space, and V is the volume. In KNN, what you do is if you have data points like this, for instance, if you want to increase, so the K means the number of data points you need to check. So you will increase the size of your volume until unless you find the sufficient number of data points. So if I have three nearest neighbors, so I'll increase it till this outer circle so that I have all the three neighbors in my point within the radius. And then what I do is I check the probability again using the same formula. But here this is variable, the volume part is variable. We fix the K, and here the volume is fixed, and we find the number of Ks. Okay, so I think we have one question on this, so we can discuss it there. And the last topic that was discussed is linear discriminant analysis. Second last topic. Why do we need linear discriminant analysis? Why can't we do away with PCA? Hmm? Anyone? What does PCA use? What kind of data does PCA use? And what is the aim of PCA? So it finds the principal components. It is it doesn't have labels attached to it. Yes. So if I have some data which is like this, and probably it is like this, it won't use the label information. What PCA will do is get this direction. Uh, what PCA will do is it will get this direction. What it finds is it finds the direction in which the projection will be maximum. So this is the specific direction in which the projection will be maximum. But the point is, once you have labels out there, you want to separate it. This is X1 and this is X2. Yeah. So once you have labels, you want to separate it out. So if you project these data points onto this direction, what happens? You can see that they are not separable. But in another case, if you have data, if you have this specific direction, and then if you try projecting the data onto this direction, what you have is this. You can easily separate the data in this direction. So that's what linear discriminant analysis does. You need to find the best uh, direction which separates different classes, and what? And separate different classes and keeps similar same class data, keeps data from same class together. So one way of measuring the separateness of different classes is what? It is the between class variance. Yeah, this is between class variance. And one way of keeping the data together is the within class variance. So yes, we will probably discuss it in the questions. So this is the main idea, and what it tries to solve is an optimization problem like this. We maximize over W such that W transpose S B into W upon W transpose S W into W. Maximize this specific quantity where W is the classifier weights. Okay, so once LDA is done, it can also be used for face recognition. That was the example given in the class. And the last topic is about support vector machine. What kind of classifier do you think support vector machine is?
It is a discriminative model. I think it gives the best decision boundary.
Best in some sense. Okay. Uh,
Margin between the classes.
yeah. So it maximizes the margin between the classes, maximum margin classifier. So what do you think? Even this LDA analysis, when we try to optimize this, it is also a discriminating model and not a generating model. So in both the cases, we are not assuming any distribution on the data points. Yes. Instead of assuming any distribution, we are just trying to deal with whatever data we have. So these are all discriminative models. But before this, all we saw here is assuming a distribution or trying to get the idea of the distribution in the non-parametric form. So that's a big difference between what we did till now. So yes, as someone said, it's a discriminating model, and you can pose it again in terms of a discriminant function. Here, SVM will be a linear classifier. So what it tries to do is, again, our colors will be used. So if we have our data points like this, and then so there are multiple classifiers that you can see can classify this set of points into correct classes. The point is, what is the best classifier? We see that generally, if there is a classifier which follows somewhere in between these two set of data points, between in the sense, if you want to do it mathematically, then the points which are closest to the points which are at the extreme, the points which are extreme are used to get this classifier boundary. Okay, so yeah, this is very brief introduction of this, and we will do an example of this question. Okay, so let us start with the questions. I hope there are no doubts. It was a very brief introduction for this long week. Yeah, so here we have the first question here. Get the feature vectors belonging to the two classes. Once we have these feature vectors, find out the projection direction that can linearly separate the two classes. So what is it that you need to do? Can anyone tell me? So you are given two sets of feature vectors for the two classes. So you need to find the projection direction that can linearly separate the two classes. So what is it? What method would you like to use? There are so many things that we discussed till now.
LED,
Hmm. Sorry?
LED,
Yeah,
LED.
LDA. Yeah, so we need to use LDA here. And how to use LDA?
We have to first find view mean and then find the covariance matrix and from SB and SW.
Yes. So, yes, you're right. So we'll first find the mean mu1. So maybe I'll write it like this. Step one is find means mu1 and mu2. I think that is very easy. Just take the simple average over each dimension. And then the step two is find covariance matrix sigma 1 and sigma 2. Covariance is for each classes. Once you have covariance, then what is it that you need to do?
SB.
So it's just the standard formulas that we have to use for the LDA case. So what is within class covariance or within class scatter, which is just the summation of these two. Yes. So this is the within class scatter or within class covariance. And the next is between class covariance. Or how does it look?
Minus B2.
Yeah, mu1 minus mu2 into mu1 minus mu2 transpose. And once we have this, we just need to, I mean, this is our cost function, W transpose S B into W transpose S W into W. Hope I'm right. Yeah, this is the one, and we need to maximize this over W. So we want to maximize the within between class variance. That means this tries to get the separability part, and this is what this tries to get the togetherness within class. Separability between classes, the togetherness within class. Okay, so within each of the class. So since you have this uh, solved there, you can use the optimal formula, which is just this. So mu1 minus mu2 we have already computed. SW is just the summation of the covariance matrix. So you just sum the two covariance matrices and then take the inverse of it. And what you get is the final weight matrix. So what is this weight matrix? This is the direction in which the data should be projected for linear separability. Yes, is it fine? Is the procedure fine? We'll just compute means of each of the class, variance of each, covariance of each of the class, sum the covariance which gives us within class matrix scatter, and this is the between class scatter from here. And what we have to use is to maximize this quantity which is solved and given to us. So what we have to do is just take the inverse of the within class scatter and take the difference of the means. And what we have is this specific direction over which you can project. Is it all right? I am not explicitly solving for these values, but this is the procedure. I hope the procedure is clear. Any doubts? Yeah.
No, sir.
No. Okay. No doubts. Okay. Fine. So we'll move on to the next question then. So maybe we'll solve this question completely. Otherwise, you won't get the feel of tutorial. Okay. So using least squares regression for the following set of points, find the value of y for x at 8. Okay. The value of y for x equals to 8. Okay. That's how to do it. What is least squares regression? So here we are doing a linear least squares regression. Linear means we will fit a line since we have a 2D data. So 2D data linearity implies we'll fit a line. Okay. So how to proceed? Can anyone tell?
Writing the error function and then finding the slope and the constant using gradients.
Yeah, so first is the line model. You define your line model like this, right? Your slope and intercept. So this is the first step. You define your model for any regression task. Here we choose it to be a line. So once you define your model, then define the cost. This is step one. What is your cost? Your cost is minimizing over some quantity, which is what? This mxi plus c minus yi whole square. So this is squares since we are doing least squares, and the least means we are trying to get minimum. Minimum over what? Minimization over what? We are trying to find the model parameters, which is m and c. Yes, your model parameters for your line is the slope and the intercept. So this is define the cost. This is the next step. Once you have this step, what you need to do? You can again rewrite it in matrix form. So I can equivalently write this as summation over I. If I take m and c as a vector, then what it turns out to be is xi and 1 is a row vector here. Yes, is this clear? And I'll keep yi in the same manner as it is. So this turns out to be something like a times these parameters minus capital Y norm squared, where a is x11, x21, like this, where each row is x1, the x component, and the 1 appended to it, and capital Y is just the vector containing all y's. Okay, so if you expand it, it will turn out to be what? Let me put this as P. So it is AP minus Y transpose AP minus Y. And once you take, so let me write this as C. C is the cost function. So once you take the gradient of C with respect to the parameters P, it will turn out to be 2 times A transpose of AP minus Y. It's just coming from calculus. So once you have this, your gradient should be equals to 0. This is the first order necessary condition. for minimum or maximum. So your second order condition will tell you whether it's a minimum or maximum. For this case, it will be, turns out to be minimizer. So once you equate it to 0, what you have? A transpose AP equals to A transpose Y. Okay, so this is the set of equations. This is the linear system of equations to be solved for our specific case of line fitting problem. So what is it that we need to do? We need to first get A and Y and then do A transpose A and then do A transpose Y. So what will be the matrix A here? So if I see these points, matrix A contains just the x coordinates 0, 1, 2, 3, 4, okay, and 1 appended to it. So it will be 0, 1, 2, 3, 4 and 1 appended to it. What about Y? Y is just the Y coordinates given to us, 2, 1.5, 0, 0.5. So if you try to compute A transpose A, just take transpose of it and do a matrix multiplication. It turns out to be like this: 30, 10, 10, 5. And if it is like this, then you can just write it as I calculated it previously. I'm just copying it here. Yeah, -1 and 3. So what you have to find is A transpose A into X. X here is P. Sorry. A transpose AP equals to A transpose Y. So our parameters P, which contains both the slope and intercept, is A transpose A inverse A transpose Y. So how to take inverse of this? Okay. It's a 2D matrix, right? Can anyone tell? What's a quick way to do it? So 1 by determinant of this determinant will be 150 minus 100 is 50. And for 2D matrix, it's easy to remember. So the diagonals will be swapped and the non-diagonals will just be negated. That's all it is. Okay. So this is inverse of 2D matrix, which is a very simple formula to remember. So once you have this, what we can do is then just get the values M and C, which turns out to be minus 0.7 and this is 2. So what our ultimate question is to find the value of y for x equals to 8. So we need to find y equals to mx plus c at x equals to 8. So we have 0.7 coming from here, x is 8 and c turns out to be 2. It gives us minus 3.6. Okay, this is the final answer. Any doubts? Okay, so
Sir,
we'll,
can you repeat again?
okay. So what we are doing is to find uh, we are doing is a least square regression for the following set of points, and we assume a linear model. For our linear model, since the given data is a 2D is in 2D, so it turns out to be a line. So what we'll do is we'll fit a line for these points. So what is the first we'll define our model as what is the line equation that we have, which is y equals to mx plus c. Once we define this model, we'll pose the minimization problem, which is the least squares. Least because we are doing a minimization, and squares because we'll to minimize the errors in a squared fashion. So what I did is just mx plus c minus y for each value of I, since we have data points xi and yi. Once we do this, I just rewrote it in terms of matrix form, which is AP minus y norm squared. Once you have this matrix form, if you take the derivative, it should turn out to be zero, which is the first order necessary condition for a given value of p to be minimum or maximum. So given this condition, we'll try for this system of equation, just rearranging terms to the right side. It is A transpose AP equals to A transpose Y. And once we have this, how did we construct this matrix A? It is just by placing the x coordinates here and then the values of 1, appending it with 1. And that gives us the matrix A. For the vector Y, we just appended all the values of the Y coordinate. That's it. So once we did this, we constructed this matrix and this vector, and then we took matrix multiplication, which gives us this value, and matrix vector multiplication. And so from this given equation, what we need is to find P. P contains both the slope and intercept, and we did inverse of a 2D matrix, which is just swapping of the odd diagonal elements, and off diagonal elements are just given by a negative sign. And then we get these parameters. Once we get these parameters, the question that they ask is find the value of y at a given point x. So we just place the values of m and c that we got, and then we place the value of x that was given in the question. So which gives us the answer, minus 3.6. Okay. Okay. So what we have is find the probability density at point x. This. Okay. So we have three-dimensional. So our next question is three-dimensional normal distribution. Of course, you are given mean and variance. How do you find the probability density here? It's very easy. So we'll first write the form of normal distribution. How does it look in n dimensions? Anyone?
1 by 2 pi to the power d by 2 into determinant of the covariance matrix power 3 by 2.
Half to the power half.
Oh, sorry,
And
power half, and exponential of mu minus x transpose, half mu minus transpose, and the covariance matrix inverse, and x minus mu.
yeah, okay. So this is just a simple formula there. And what we need to do is, for the case of d equals to 3, since it's a three-dimensional normal distribution, we'll just replace the values. So this is 3 by 2. So this is sigma. What will be the determinant of sigma? 25 minus 4, 21, right? So this will be square root of 21, exponent of minus half times x is something that we have to find. This is given to us. Mu is given to us as 1, 2, 2 transpose sigma inverse. So this sigma has a special structure. If you see, we just have this block diagonal which has values. Other parts are just like identity. Can you guess how the inverse look like? So this part is coming from the identity matrix. So this part, even after inverse, should be an identity. Yes. So generally what we do is we divide it by determinant of the matrix. So we'll keep the determinant here and keep the rest of the zeros there. So that ultimately this into this will give me the identity matrix. Okay. What about this part? This part is just a two-dimensional matrix. Again, we'll use the same thing. We'll swap the diagonals and negate the off diagonals. So this turns out to be sigma inverse. You can just check it. Multiplying this matrix with this gives you identity. Okay. So again, we'll finish the equation. It is x by 1 to 2. Yeah, this is the equation. And once you place the value of 0.50 and 1 here at x, 0.50 and 1 and this value of x, what we get is 0.0088. This is the value. So for this, anyways, you have to use calculator to get the exponent. This you have to compute what scalar it is, and once you have the scalar, you can use calculator to get exponent and get the square root of 21. And this part. Is this question clear? It's just getting. Uh, it's just about how to use the Gaussian function. That's it. There's nothing more to it. Okay, so we have next question there. I hope this question is clear. No doubts in this question. Okay, this is weird. Okay, I'll just try. Normal is class W1. Mild fever class W2. COVID-19 fever is class W3. Okay. Okay, yeah. So this should be fine. I'll read out the question. So we had enough of COVID. I guess everyone is fed up of it. The ICMR considered human body temperature as the prospective indicator for disease, and based on the thermal reading of the body, there were at the two quarantine centers, they decided that they'll classify the the body temperatures as normal or mild fever or having COVID-19. So once you have this classification, they collected data samples for each of the class, which belongs to class normal, which is this is for normal, and mild is this specific data, and the third data is for the COVID. So they are measuring temperatures. What do you think would be the unit of these temperatures? Just a side question, but
Fahrenheit.
yeah, it should be Fahrenheit because if it's degree Celsius, probably humans will die at this temperature. Okay, so these are all given in degree Fahrenheit. Uh, that's just a side note. Yeah. So all given these three data, given the three classes and their data points, and they have equal prior probabilities. That is also given to us. The first part of the question is we need to fit one Gaussian for each of the data points for each class. That is estimate the class conditional probabilities. Okay. So once we do this part, and then we'll move on to the next part. Okay. So how to proceed? What is it that we need to get? What is class conditional? Density. How do you denote it? Probability of x given Wi, right? And how do we write it? Anyone?
Probability of omega I given x into probability of omega I given x is equal to 1.
No, no, no. You don't write the posterior in terms of prior. I mean the class conditional density. What you told probability of omega I given x is a posterior probability.
Oh, yeah, sort of got confused. Sorry.
So what we have this, we are directly modeling it as Gaussian distribution. So that's what I was asking. So what we need to do is just write Gaussians. That's all. So these are all one-dimensional data, right? This is just one dimension. So I'll write the one-dimensional Gaussian. So here it will be sigma I, and here it will be mu I square upon sigma I square. This is the one-dimensional Gaussian, right? So now you have to do it for both, for all three cases of I equals to 1, 2, and 3. Yeah, that's all we need to do. So how will we get it? So what we need to find? We need to find mu I and sigma I. So mu1 will be what? Just sum these and take the and divided by the number of samples. So mu1 will turn out to be uh, summation over I belongs to, or rather xi belongs to wi. Just writing a general formula divided by number of elements in class wi. So my notations are like this. And once you get mu I, the sigma I will be again sum over the same set xi minus, okay, there is xj. I will write it as xj so that here divided by number of elements. Okay, so this is the usual mean and variance formula. Yes. So what you need to do is just place these formulas for each of the class, and what we get is these values which I pre-computed. So what will be the unit of mean? Since I told the unit of data points is in degree Fahrenheit, what should be the unit in mean? Anyone? The units of mean should be?
Fahrenheit.
Yeah, it should also be in degree Fahrenheit. This is the units. What about the variance? What should be the unit? Hmm? Anyone? Or if you can say what should be the unit of the standard deviation sigma, then it's easy to get the units for variance. What should be the unit for the standard deviation sigma? Should also be in degree Fahrenheit, right? Everyone agrees? So whenever you do a measurement, so your final quantity will look like this, right? X is some mu plus sigma. Your X is the quantity that you wanted to measure, but this is the mean of the observations and this is the standard deviation of the observations. So that's how you write it. So this mu and this sigma are in the same units, and about sigma square, of course, it should be degree Fahrenheit square. Okay. So these are just small things that one should take care of. Okay, so once we have this clarity on these units, so we got the means, variances, and standard deviation. What we did, we found the Gaussians, specific Gaussians. We can just replace the mu and sigma here in this expression, and we get the specific Gaussians for each of the class. So now the second part is for a new person. Why we did all these things? Because for a new person, we want to detect whether that person has mild fever or COVID or easy normal. So the new person has a temperature of 101.2 degree Fahrenheit. Consider the minimum error rate discriminant function. What is the minimum error rate discriminant function? And find out which class it belongs to. Okay. So what is the minimum error rate discriminant function? Hmm? It is the base classifier. Yes, it reduces the error rate and it is optimal. The base classifier is optimal in the sense that it reduces the error rate, or rather gives you the minimum error rate classifier. Okay, so what is the base classifier? We need to find the posteriors. This is what we need to find for base classifier. And for this, we'll use this is the posterior. Once we have this posterior, what we have is this is class conditional density, which we just computed now, which is this expression with these specific values there. And once this is done, we have priors for the class, which is what? Which is given to be of equal probability. So that means all of them will be same. And this is the evidence, which is not really required for the classification. Okay, so what is the priors for the class? What would be P of Wi? So we know that it's same for all the three. So this implies P of Wi will be 1 by 3 for all values of I is 1 to 3. Yes? Do you agree?
Yes,
Why?
because every person beforehand we do not know that whether that person has, so we could put him in any of the boxes.
So there are only three possible classes. So the summation should turn out to be 1. And if all the terms in the summation are same, then it turns out to be they are equally divided. Yes? This is the main thing. For our case, it is I equals to 1 to 3. Okay. So that's why probabilities for all the classes are same. Okay. Yeah. So what we need to find is the posterior. So since we are asked to use a discriminant function, so how do you design a discriminant function from this posterior? Is simply writing the posterior as your discriminant function. Yes. The higher the posterior, the higher will be the value of this discriminant function. That means it will be your way to decide which class it should belong to. Or you can use this, or you can do a nonlinear mapping as well. What people generally do is take this specific value. This is the most often used value, uh, often used. discriminant function. Well, here we are using P of Wi given X because we are using base classifier, and base classifier is the minimum error rate, but the inside quantity, or rather the whole discriminant function, can be defined in a different fashion. Okay, so given this ln of P of Wi given X, what is it? I'll just expand it from this expression, which is ln of P of X given Wi plus ln of P of Wi plus minus ln of P of X. Yes, I've just taken log, and multiplication and division is given by plus and minus in the log space. Okay, so given this, what we need to do? We know that this is same for all cases. So this is a constant and this is a constant, and that constant is independent of the class because P of Wi is equals to 1 by 3, which is independent of the class I, and Px is same for all the GIs. So what we can do now is I can just write it as P of X given Wi plus some constant which is independent of class. That's why I'm writing C and not Ci. Okay. So what next we need to do is we need to find P of X given Wi for I equals to 1, 2, 3. So that's how we'll get the probability there. So since we have the specific values of mu's and sigmas, we should be able to place this value and place the value of X. X is here 101.2 degree Fahrenheit. And once this is done, we can get these values, which turns out to be, yeah, 9.456 into 10 power minus 3. Point 059. Okay, so now what I need to do is I'll just get the equivalent GI of X, right? So this is G1 of X, which is ln of 0.9456 into 10 power minus 3 plus C. G2 of X is ln of this quantity, and G3 of X is ln of this last quantity. Okay. So now from given these three values, can you say anything? Which class should this X equals to 101.2 belong to? Anyone?
Class 2.
Yes. So we have to compare these three values. So we can see that at X equals to 101.2, these constants don't matter because they're all same. G2 of X is greater than G3 of X, which is greater than G1 of X. Yes? Everyone agrees? Why am I saying this? Because why? Because log is monotonically increasing. Or rather, I should write ln log base to the log to the base e function is monotonically increasing. So once you have this monotonically increasing function, if you know that the input values are in this order, uh, x1 is greater than x2, then log e of x1 is also greater than log to the base e of x2. So that's why I'm directly saying given without computing these values. Okay. So your final answer is it belongs to class 2, which is mild fever. Any doubts? So this problem is fine, right? It's a bit lengthy problem, yes, but at least it gives you an idea of how to use the data in real life. Okay, so we move on to the next one. Hmm. So you are given a Gaussian function with sigma this as window function. Okay, so given a set of 5 data points, so you have this 5 data points 2, 2.5, 3, 1, and 6. Find the Parsons probability density function estimates at x equals to 3 using the Gaussian function. So you need to find the PDF using the Parsons window method. Okay, so how do you do it? How does Parsons window work? This is what probability of x, the PDF of x given n data points. Yes, so this formula was discussed in the class. I'm just rewriting it. Is I equals to 1 to n 1 by v, and this phi is a function x minus xi upon sigma. Okay, it should, I don't think it should be written like this. I will try to rewrite it in this x minus xi and the function. It's fine actually, doesn't matter. Okay, so this is what? Normal distribution. So what we have is we have normal distribution at each given point xi, and we sum those normal distributions uh, given by some weights, and we average it out. And what we get is the probability of the given data at that point x. Okay, so how will you do it? Just replacing the values x minus, for x I'll take x equals to 3, and for xi it should be, for first instance, x minus x1 upon sigma turns out to be 1. So this probability is just the Gaussian distribution. Sigma is 1, so we can easily write it as x minus x1 squared upon 2. Okay, so this value turns out to be 0.242. Again, phi of x minus x2 upon 1. This value turns out to be 2521. Phi of x minus x3 comes out to be 0.3989. This is 0.0540, and for the last one it is 0.0040 probably. Yes, just check the values. It's just taking exponentiation and dividing it by root 2 pi. Okay. So once we have these values, what we need to do, we'll just place it here. Yes. Just give me a minute. So that's all you need to do. So here you can take v to be 1. Since there is nothing given about the volume. Yeah. So there is nothing given about the volume. So what you need to do is just average out the 5 numbers that we got it. Okay. So once you average it out, this will be En of x is 1 by 5 of this summation over 5 of x minus xi or I, which gives some value, it's 0.210. Okay, any doubts in this question?
Do we choose the value of v according to us, or is there some expression for it? Because I saw something like sigma to the power d, and I, I'm not sure about that.
Uh, where did you see the expression? Is it given in class notes by any chance?
No, another NPTEL course which covered Parson window
Okay, okay.
function.
Yeah, actually, this v should be the normalizing factor in such a way that this turns out to be a probability distribution, Pn of x. Otherwise, just taking the averages of normal distributions will not help. So, under ideal conditions, you would have to integrate it. Yeah, I mean, you can just take v to be constant. So, you can just take 1 by v of this other things in this expression and integrate it so that it should sum to 1. Integrate over all values of x so that it should sum to 1. So, that's how you get the value of v. And I think most probably that's how they calculated v there.
Okay, thanks.
Yeah. Okay. So yeah, but for this course, you can just use v as one, just for computations. Okay. So we then move on to the next question. So the next question is based on SVM, support vector machine, that we skipped very quickly during our discussion. So what does this question say? So we are given a set of training samples x1 and x2, and we are given their labels, whether it's a positive sample or a negative sample. So once we are given these labels, you are also given lambda i's. What are the lambda i's? They are the dual variables, or the KKT variables. Okay, so only so if everyone remembers this, so how to get SVM? Well, in the marginal line for the classification. Okay, so what we need to do is find and fit an SVM model. So this SVM model as such is given like this. It's again a linear model W transpose X plus B, but the weights uh, W are obtained from summation over I belongs to the support vectors lambda I yi xi. This is how the weights are obtained. This is the yi there, this is lambda I, and this is xi. And about there is another constraint which is coming from the KKT conditions, which is yi times w transpose xi plus b is 1. So if you remember clearly, this states that if we have a classifier like this, uh, so this states that whatever classifier we have should have some minimum margin on both the sides. So this is the margin on both the sides, and the margin should be maximized. That means margins on the both sides should be maximized, which turns out to be that both the sides the margin should be equal. Okay, so this is the condition that is given by KKT conditions, and this is that's something that was solved to get the weights for the SVM. Okay, so what is support vectors? The support vectors are only these specific vectors. So these specific vectors which are just touching the margins are the support vectors. Okay, all other vectors are non-support vectors. So for support vectors, the lambda I will be what? Lambda I will be positive. For support vectors, lambda I will be greater than 0. For non-support vectors, lambda I will be 0. Because if you remember the condition, there was another KKT condition that lambda is greater than equals to 0. This is coming from KKT. So it can either take positive values or 0 values. It cannot take negative values. For support vectors greater than 0, that's all we need to consider for our computation. What we need to do is just simply replace values for W. So W is summation. I'll remove the summation and directly write values. Both are 65.52. Okay. The lambda is 65.52. This is lambda 1. And W, now yi is positive. So it is into 1 into this vector, which is 0.38 into 0.38 and 0.47. Okay. So this is x1. Again, 65.52 into minus 1. This is y1. This is y2. Lambda 2. Yes. And this is what we get here is from is 0.49 and 0.61. Well, you can also use other vectors. The point is you can clearly see that the lambdas are 0. So even if you add them, it doesn't matter. So this is how you get the weight vector for the SVM, which I think turns out to be minus 7.21 and minus 9.17. You can just do the calculation. Once you have this is x2. Y2. Okay. So once you have this, what is the next thing that you need to find? You need to find B. B for the classifier. How do you find B? So we have this constraint equation here. Yes. Yi times W transpose Xi plus B should be equal to 1. So if I do it for the first case, Y1 W transpose X1 plus B equals to 1. Or I can equivalently write it as, I'll just write the step, which is Y1. Does everyone agree with this? Why? Because Y1 belongs to minus 1 or 1. So if I multiply Y1 both the sides, will look like this. Yes, Y1 square of this, and this is Y1. So y1 square will always be 1. This will always be 1, which gives us W transpose x1 plus b equals to y1. Else, we can also write it like this, y1 minus W transpose x1. This is what we need. Okay. So similarly, we can also write compute b from y2, which is, so if you compute b from y1, it gives us 8.05, and if you compute b from y2, it gives us 8.12. So here in this question, the problem is the numbers are not accurate enough. There are some approximations done. That's why you are getting two different y's uh, with different data point. Otherwise, what you get is both the b's should be same. Both the b's should be same. Although they are close enough, you can see that, but they are not exactly same because the w computed is not accurate. They are truncated up to 2 decimal places. So you need to have higher precision accuracy to get them same. Okay, is this question clear?
Yes, sir.
Okay, we will move on to the next one. Uh, Next one seems simple. Uh, so yeah, suppose that x is a discrete random variable with the following probability mass function. The theta is the parameter. As you see here, theta is the parameter for the probability mass function. The following 10 independent observations were taken from such a distribution. Okay, so these are 10 observations from the same distribution taken. What is the maximum likelihood estimate of theta? How do you write maximum likelihood estimate? The probability of x given theta is, so they are independent observations, and of course they are coming from the same distribution. So we can write it like this. This is for independent observations and identical distributions. That's the case where you can directly like this, write this. If they're only independent, then you have to write it individually like this. And if they're not even independent, then you don't hope to use MLE at all. It's that problematic. Okay. So assuming that you have 10 independent observations and they are taken from the same distribution, you can write it like this. What does it say? I equals to 1 to n. So probability of xi given theta. So xi is what? The first xi is 3. Yes? Rather x1 is 3. This is x1, this is x2, this is x10. So first x1 is 3 means for x1 is 3, what is the probability? It is 1 minus theta by 3 into the next one. So for 0, it is 2 theta by 3. For the next one is 2. For 2 is 2 times 1 minus theta upon 3, and so on. So just write the equivalent probability corresponding to each of these x's. So which is, you can directly write it as how many times 0 occurred, just power it. So 2 theta by 3 to the power, how many times 0 occurred? Twice. And the next is theta by 3, how many times it occurred? Which is 3. And similarly, yeah, 2 times 1 minus theta upon 3 occurs thrice, and 1 minus theta upon 3 occurs twice. That means 3 occurs twice. Yeah, that's why I'm writing this 2. So this is for x equals to 0, x equals to 1, x equals to 2, this x equals to 3, and this is number of times they occur. Okay, once we have this, we can just solve for this. How to solve for it? We take log of the likelihood. This is the likelihood function, right? Once you have this likelihood function, you take the log of this, and which simplifies many things to a good extent. So this is ln of 2. Just take log over this part, and then log over the next part, and then log over the next part, which is log over the final part. So once we have this, you can just rearrange them, which turns out to be some constant coming from these numbers, plus 5 times ln theta plus 5 times ln of 1 minus theta. So what we need to do? Maximum likelihood estimate. Maximum means take derivative. So derivative with respect to theta of ln of p of x. Yeah, theta. So this turns out to be 5 by theta plus 5 by 1 minus theta into minus 1. And this derivative should be 0 for a maximum or a minimum. If you take double derivative, you'll see that it's a maximum. So this gives us theta as half. Okay. Is this question clear?
Yes, sir.
Okay. So, okay. There's another question on principal components that we did earlier, so I'm not doing it now. So we'll just move on to last question for today. Just this one. So given that we have two attributes for a particular product in the company to classify whether it's a good or a bad product. Okay, so there are four training samples. In general, four training samples are very bad because you need many, many more samples to generalize properly. Okay, so given these two attributes x1 and x2, they gave the labels whether it's good or bad. Now the company wants to produce a product with x1 as 3 and x2 as with this attribute of x1 3 and x2 as 7. So use KNN algorithm to determine the class of the proposed product. Take k is equal to 3 and use the Euclidean distance for the measurement. So how to proceed?
Take three nearest points and do the voting accordingly.
Yeah, right. So how what to do in the first place? So we need to find the nearest points. For that, we need to compute distance. So the step one is compute distance. So what should I say? Let this new thing is some z, and these old things are z1, z2, z3, and z4. So the distance between z1 and z is z1 minus z squared. I'll just take the square distance, which is 7 minus 3 4 squared, 7 minus 7 0, and the next is z2 minus z squared, which is 3 square plus oh, 4 square plus 3 square. This is z3 minus z squared is 0 squared plus 3 squared. I'm just taking a Euclidean distance, 3 minus 3 0 and 4 minus 7 3, and just squaring it. And the last one is z4 minus z squared, which is 2 squared plus 3 squared. Yes. So if I just write this, this will be 16, 25, 9, and this is 11. Oh, sorry, 9 plus 4, 13. Okay. So given these distances, well, this is distance squared, so we can just use this directly instead of taking a square root. What do we need to do? We need to check k equals to 3. That means what are the three nearest points from this query point? Query point is z. The three nearest point is 9, 16, 9, 13, and 16. Okay. So given these are the three nearest points, what is it that we need to check now? For 16, we know that the point is bad. So this is a bad point. Second one is not required. The third and fourth is good points. Once we have these good points, so we take the majority vote. So the majority vote gives us a good point. So this point should be in the good class and not the bad class. Okay. So the class determined is good. Okay. Is this part clear?
Yes, sir.
Yeah. Okay then. I'll see you people next week. Thanks for joining and sorry for being slightly late.
Sir,
Okay.
I have a one question.
Yeah.
Question number 9 of assignment. Can you please explain how to solve in short?
Nine. Okay. Can you just tell the question because orderings might not be the same.
Yeah. Let us consider a 3D feature vector for a two class problem W1 and W2. A
Okay. This
prior,
one. Okay. Okay.
yes, sir.
Okay, yeah, this question doesn't seem to be stated properly. So if they are given PEI as zero point 0.7 and QI as zero point 0.4, what does it mean? I don't understand. And then they define PI as every component of feature vector has a probability of being equal to 1 is zero point 0.8. If it's fine, can you just post it in the forum? Because I did not create these questions. So the question and the people who created the question can give you the answer.
Okay, sir. Thank
Yeah,
you.
because there's just, I mean, the writing is not correct. So even I clearly don't understand what it.
Okay, sir.
Yeah. Okay. So I guess there's one more question that was left, which was PCA one. I think that should be very easy. We did it previously as well. Okay. Yeah. Okay then. I'll see you people next week. Thanks for joining. Bye bye.